Thank you for attending, everyone, today. And we've got Peter here. Peter is a fellow of the IStructE and author of Computational Engineering, which can be purchased on the IStructE website for those that are interested. But not only that, he's also the chair of the Yorkshire Regional Group. And today he's going to be speaking about his experiences with computational analysis, as well as common mistakes and how to avoid them. So over to you, Peter.
Thank you very much. Today we'll be looking at modeling, checking errors, and maybe some further reading advice. We'll be taking questions at the end, so you can put the questions into the chat box, or we can do a microphone unmute at the end as appropriate. So first of all, getting things right. So there are many things to consider when you are working on an FE model. This is going to actually advance. There we go. So PowerPoint playing up. So first of all, the dimensions of the model. The three dimensions, in fact. One-dimensional models. We'd be just looking at a single beam, multi-span beam, composite beams, that sort of thing. Best looked at when in just the one-dimensional model. I think that's two-dimensional, but yeah, a one-dimensional model. Then you have the two-dimensional models, looking at just a wall, a plane strain, what's plane stress? Plane strain analysis, that's the one. Through the retaining wall, some of that, or a tunnel, or a portal frame, or just a single floor. And then you have the full 3D models. You're looking at a whole building, or maybe a floor plus the columns, or something like that. And it's important to remember that most programs use a default to 3D, which means if you build just a single beam element in the model, you can be unstable, because a 1D model assumes additional restraints, no rotation in plane, no movement out of plane, and that sort of thing. So there's the three dimensions of the model, which is a choice, but you also got the three dimensions of the element. So we have the one-dimensional elements, the standard, the framing, the beams, do everything, bar elements, axial only, links, infinitely stiff elements, springs, which have defined stiffness, and various others. Two-dimensional elements, typically shells, for modeling walls and floors, also plane stress elements, which have in-plane stiffness only. And you can have the 3D elements, bricks, tetrahedrons, and so on, for doing solid modeling. In structural engineering, we tend mostly to use 1D and 2D, but 3D is an option in some programs, and can be good. Downside is you only get stress output from 3D elements, and if you want bending moments and shear forces, then 1D and 2D can be more useful, and also can be more practical, because it depends on what you're doing the model for. So let's say you're modeling a steel frame. Classically, 1D elements for everything. Simple connections, pinned ended beams, or moments releases on the ends of the beams, maybe bars, axial load only on the bracing. And because in a real steel frame, you've often got a concrete diaphragm. You could model the slab in explicitly, but to be honest, that will actually confuse things. So some sort of rigid constraints over the whole floor to keep things stable and give that horizontal load transfer to the bracing. Also, unlike the CAD programs, you want the beams on the centroids. Offsetting the beams down the top of steel, for example, that can add in some weird additional effects. So by default, keep everything on the centroids. The exact level is not normally that important. So the top of steel for the centroids is close enough for engineering in general. Can make a slight difference once you get to the columns at ground floor level. Just something to watch out for, that the columns at ground floor might be yeah, just double check the lengths on those when you go down to the foundations. So steel frame, and then concrete frames, slightly different. Concrete frames, especially beam and slab arrangement or a flat slab especially, you would include the slab explicitly. If it's in situ concrete and the beams and the slabs are working integrally together, you could keep the beams on the centroid if you want them to just act as rectangles. If you want that T action, you can be offsetting the slabs up and the beams down, or explicitly modeling T sections and watching out for the overlap of the two. Just remember, if you do start offsetting the beams and slabs, you will get in-plane forces in the slab, and you will need to make sure that that is designed for. Also, concrete cores. I mean, you could have concrete core on a steel frame. In this situation, you'd be looking at modeling the core in 2D elements, so shell elements to pick up all the local effects on the core. Whereas, of course, if you're modeling at scheme stage, keeping it really simple, you could do the whole core with a single a column of 1D elements. So the 1D element represents the core as a whole. Sometimes people have, especially in the past, used 1D elements for the aspects of the core, you know, a column on each wall face. That's not done much these days. Yeah, before we had 2D elements commonly used, that was the way forward. These days, I don't think I'd bother. I'll go straight for 2D elements and then use assemblies or similar to collate the forces together. Now, if you are modeling beams and slabs or shells together in the one floor plate, you will notice some slight differences in the bending moments. For example, here you see the bending moments are not quite as smooth as you'd normally expect. That's because the beams and the slabs are interacting with each other, even though they are both on the centroid in this particular model. If you were offsetting the slabs, then there will be the in-plane forces as well, and you need to look at those forces in addition when you're looking at the results. There is a wide range of choices for analysis, and the analysis can affect the way that you model. So most of the time we're modeling for linear static analysis, and we use those for working out what the section sizes will be. If you're then looking at p-delta effects, nonlinear analysis, buckling, dynamic analysis, so on, we need to know what the correct section sizes are. So this sort of analysis will come after the linear analysis. We design the sections, we then double checking in a bit more detail for the various effects. Now, also, when you come to dynamic analysis, maybe things like the end connections might be different. So a steel frame, typically moment releases on the ends of the beams, but for, say, a footfall analysis or a buckling analysis, you might be assuming they are fully fixed. So slight difference in model, and likewise, some vibration image there. But for footfall analysis, you might have cladding around the outside, and that would actually provide a restraint. So we've done the model. Then we've got to check validation and verification in full detail, but checking overall. So when do we check models? Every single time. The reason for this is mistakes do happen. We all make mistakes in various forms, and as we're looking at buildings or bridges, these can have serious consequences. Now, there are a number of aspects for checking. So first of all, validation, which is essentially making sure that you're asking the right questions. You don't build models because your student engineer asked you to build a model. You don't build a model because you like to build models, though they are fun. We build models to answer specific engineering questions, and the model must then supply the answer to that. So, first of all, valid software. Is the program that you're using suitable for the problem in hand? Can it actually address the problem? If it's not explicitly designed for that problem, you might need to either get a different program or use a program very cautiously with a lot of engineering judgment to say, okay, this is probably all right, or maybe not. These are there to inform you as to how the structure is working. And maybe it can, maybe it can't, but you have to be sure that you're using the right software for the problem you're looking at. And then, of course, there's a valid model. Is the model built to answer the question? And as a model builder, you've got to know what the question is to make sure you then build the right model. This does come with experience. Invariably, when you first start modeling, they're far too complicated because you don't really understand what to include, what you can leave out. With experience, you can build the models more and more efficiently, more elegantly, more correctly, to give you the correct behavior, because that's what the models are all about. Getting the right, not the right look, the right behavior. So, and there's also then, validation and verification, which is essentially making sure you get the right answers. Again, you can verify the software. Can the program give the right answers? Now, the software manufacturers, they will be doing this as well. This will be a main area of their work, or should be if they're professionals. But it's also good practice for you to run a few test models. Make sure that you are getting the answers you expect. Because yes, and verifying the model. Does the model give you the right answers? Which is a curious thing to think about it, because we're building the model to give the answers, but we also, as engineers, should have a very good idea of what the answers should be, at least approximately. Maybe not full detail, but have a very good idea. So under gravity, we expect things to deflect downwards, for example, and so on. And the way I like to remember about verification, what it means is, verify. Yeah, it's got the word error in there, sort of. So it's looking for errors, making sure we get the right answers. So what happens if the model doesn't give the answers you expect? What might have happened there? So it may be that your model is wrong. It may be that your assumptions are wrong. It might even be the software is wrong. But it's not normally the software, unless, of course, you've written yourself, or one of your mates has. Then there's a good chance that that will be wrong. But yeah. And then so you've got to have an expectation of what the model should be doing before you start modeling. Because if you don't know what the model's going to do, then you've got no idea whether it's right or not. And you then have to rely on your colleagues to try and spot that for you, which is always embarrassing. No one likes that. And of course, when you get to doing the chartership exams, which at this point, doing the exams, you don't have access to the computer. You've got to demonstrate that you do know the answers as part of the exam. So it's really good practice for the chartership. So how might you go about making your assessment? So one option is just produce a simpler version of the structure. So for example, you're modeling a truss. A truss is essentially a beam. slightly more complicated, but in principle, it is a beam. If we were analyzing a beam by hand, you'd use WL squared upon 8 to work out the bending moment. And from the bending moment, you can divide by the depth of the truss, D, to then give us the maximum forces in the top and bottom boom of that truss. Similarly, the shear force, WL upon 2, then by the times by sine theta, which is the angle of the end diagonals. That's the shear force in essence. The deflection of the truss. The I value of the truss is a little more complicated than but there is the parallel axis theory, which means you look at the I values of each of the chords plus the separation of the chords, and that gives you a good indication of the I value overall of the truss. Note, of course, that is just the bending stiffness of the truss, doesn't include the shear stiffness or the effects of the diagonals. So it won't be exactly the same as the computer analysis, but it should be very similar, which is what we're looking for. If the results are similar, then you can feel confident. If the results are wildly different, then you know that something's definitely wrong somewhere. So how do we go about this? So look at the results. Does the display shape look correct? Is it bending in the way that you expect it to do? Does the bending moment diagram look right? The stress distribution, the shear forces, this sort of thing. Bending moment example, always in British parlance, always are shown on the tension side. So in general, the outer curve of any beam or column will be where the bending moment goes. Not always if you're dealing with thermal loads. Thermal loads are a little bit different, but general gravity loads, this is where you expect the bending moments to go. And if you look, there is a direct correlation between the bending moment and the bending of the beam. Surprise, surprise. Take a look at that. And similarly, very good exercise. If you're looking at the frame, sketch out beforehand how you expect the deflection to look. And once you've got the curvature, you can then get the bending moments, at least in principle, even if you don't have the numbers. And this gives you a good guidance of when you look at the results and go, yes, that looks promising, or no, that's not what I expected. Discontinuity in the results. Are there sudden jumps or breaks or things like that where you don't expect them? These can be major clues to problems. And if you know there's a problem somewhere in the model, but you can't work out where, break it down. Cut the model in half, copy the model, and look at that bit or so on. Divide and conquer, as they say. And after that, where next? Separate hand calculations to a reasonable degree of approximation. Beam approach for trusses, as I mentioned. Similarly, tall buildings are essentially cantilevers. You can look at the wind load onto a cantilever, take the wind load of UDL on the cantilever, what bending moments and shear forces does that give? How does that then relate to the forces in the bracing, the forces in the core, and that sort of thing? If it's a complicated model, build a simple model as a check. A space frame is sort of like a slab. A truss is sort of like a beam. A complex, stadia roof and walls in trusses are sort of like beams. Build a comparative model. Are they similar or are they completely different? And then, of course, you get the Cat3 approach. Build the model again in a completely different software, especially if you're checking somebody else's. Comparing like with like is, very useful. And again, if the separate model is similar or the same or close enough, then that's great. If they're radically different, there's a problem somewhere. Could be in the modeling, could be in the software, but you know there's somewhere to look. You do not just blindly accepting the results. Now, you found there are errors. Where might these errors be coming from? When I'm supporting my users, they say my model's wrong, I can't work out where something's up. First place I'll look is the units. This is possibly the most common area of errors. People getting confused between millimeters and meters, kilonewtons and newtons. And basically, if your results are off by thousands, a million, a billion, these are most likely unit errors. Yeah, your beam or bridge has deflected by kilometers rather than millimeters. Yeah, you've got the units wrong somewhere. Could be in the dimensions of the model, could be in the loading, could be in the sections, you name it. Yeah, likewise, yeah, displayed sections could be very, very thin. Yeah, you expect them to be in meters, but you've actually millimeters. They're very, very small. Or maybe if they batch all together, which one from I've had, yes, the dimensions of the section went in as meters rather than millimeters, and I couldn't see the sections because I was actually inside them all. And software often only shades from the outside. Ill conditioning. You've got an answer, but the answer's not very good. One area of ill conditioning is if you've got a very wide range of stiffnesses. Some very unstiff elements and very high stiffness elements. These can throw off the mathematics of the analysis. For example, in this example here, the short beam is over 15,000 times stiffer, the EI of that short section, or EI over L, I should say, is orders of magnitude stiffer than the long thin beam. This can affect the results. Non-linear analysis is even more sensitive than the linear analysis. There might have been, let's say, some very low stiffness elements. You might have adjusted the parameter of the section to say, well, there's a section, but actually I'm only going to assume 1% stiffness, or maybe 0% stiffness, or maybe the materials have the Young's modulus changed, or something like that. Zero stiffnesses invariably will cause problems. You might get answers, you might get an error. If you do get answers, they're not to be relied on. Check the total loads and reactions. Sum up the total loads, sum up the total reactions, take one away from the other. They should be 0 or pretty close. I'll not be exact due to the complexity of FE analysis in a big model, but they should be pretty darn close to cancelling out. Likewise, equilibrium at nodes, equilibrium on elements. They should all be, all the forces should cancel out on any part of the model, or at least close enough. Connections. Yeah, you get the connections in the model wrong. You might not join the model up. Rather than having shared nodes, you might have coincident nodes on top of each other. So they look together, but actually are not. Or you might over-release something. So, for example, you might release all the bending moments and all the shear forces on the end of the beam, meaning something that actually is disconnected. You might get errors from the analysis engine saying there's a mechanism in there. You might get deflections in unusual places. Look at how everything is connected together. Likewise, restraints. Again, model not joined up or connected properly. Columns can be over-released. So in this example here, I've shown some beams, steel beams framing into a column. Beams got pin ends. The column's got pin support. That column is actually torsionally unrestrained. It has zero stiffness about its axis. That could well cause an error in the analysis. The fix, you put a ZZ degree restraint onto the column. And let's face it, column base plates have 2 or 4 bolts. They will resist rotation of the column. They might not expect any loads, but yeah, they will give restraints. And this is a very common error for a steel frame. Zero load in the columns. I've seen this. People occasionally get confused between restraints and releases. They both begin with R, but a pinned restraint on the end of a beam will generate a reaction. It's fully restrained. It doesn't move. A pinned release will release the moments from the continuity. Deflections in unusual places. Again, are things you thought were restrained but actually not. Look at the deflections. Actually, animation on deflections can be very good for spotting things flapping about which you weren't expecting. Also good to remember, you must include sufficient restraints to prevent rigid body motion. You might only have vertical loads on your structure, but you still need horizontal restraints. You cannot allow zero stiffness horizontally or rotationally. I mean, the mathematics just doesn't work for starts. So you do need to make sure that you have restraints to prevent the whole thing moving. You might not get reactions there, but you will get results. And in fact, and on that note, always do check reactions, both moment and forced reactions. Are they where you expect? Are you getting reactions you didn't expect? Speaking of things you don't expect, torsion. I've made studies on where things have gone horribly wrong on structures as a result of FE errors, and torsion often features. As structural engineers, we don't deal much with torsion. Now, for example, you might find moments are going missing. So this is a model recreated from a case study I've heard about. I've actually seen the real thing, but in this, there was a project, I think it was in London, ground beam structure on piles, masonry walls going in. The engineer had used an FE program to give the loads, bending moments, and shear forces on the beams, designed for those by hand, but hadn't spotted weirdness that, for example, you see on some of those beams, there are bending moments on one side of the beams, but on the beams they're joined to, there is no bending moments. These bending moments are vanishing because they've actually gone into torsion, and the engineer concerned didn't check for torsion, didn't look for torsion, and the beams were not designed or detailed for torsion, and so they failed in construction. So the framing arrangement can give torsion on beams. Shelf angles on perimeter steel beams can give torsion. I-beams don't like torsion. Make sure you do design for all the forces and moments, major axis and minor axis, shear, torsion, etc. Make sure you check for everything. Do you get torsion where you're not expecting it? Does your structure actually require torsion to function? These are all things to watch out for. Envelopes. So when you're looking at maximum min values from envelopes, some programs, which I won't name, don't get this right. So here is an example given to me by a friend of mine from the program he was using. Values on the left, there were two reactions on the bottom of this column, which showing in the black arrows. You see on the left. And when he took the envelope, the maximum min values, the program took the maximum values for the maximum result. It took the maximum in the x direction and the maximum in the y direction, and then gave them together. And the maximum min values were actually less than the maximum individual values, which luckily he spotted before designing for those. Yeah, a good program will actually go through each individual permutation and return the maximum values for those. But remember, if you add up forces and moments which are not acting at the same time, then you might not be designing for the actual maximums. So that is something to watch out for. Linear and non-linear effects. Yeah, if you're designing using, or your analyze, well, if your analysis, if you're using a linear analysis, that's not there. If you're using a linear analysis, it will assume that the deflection is small, and it does that by establishing equilibrium at the original undeformed position. But if things are moving a lot, then that is not up to scratch. So you might want to do a P delta analysis, sway sensitive frames, for example. The sway, the deflection introduces an additional deflection, the delta time to force gives additional moments on the structure. Very large deflections, buckling of structures. These are things which won't be picked up in a linear analysis, but require a more specialist analysis to look at those particular aspects. You might have material non-linearity. Steel, for example, stresses might pass the yield limit. If that happens on a linear analysis, you know the answers won't be right. You have to run a non-linear analysis to take into account the yielding effects. And also you can have directional non-linearity, which is not an easy word to say. Compression and tension only elements. Some linear programs can deal with these through iteration and so on, or you might need to run a full non-linear analysis. And of course, when you are dealing with non-linear analyses, you must not combine the results. Doubling the load or 1.5 times the load will not necessarily give you 1.5 times the moment or the force. You have to analyze these problems with the factored combined loads to give you the right results. They are non-linear, and which means there's not a linear relationship between the loading and the results. Mesh sizing can affect your results. Here are three identical floors, identical loads, apart from the mesh size. Bending moments on the left, deflections on the right. If the elements are too big, you won't get accurate results. Conversely, if you make the elements too small, then you can get, it might be good deflections, but the reactions could be completely wrong. So for example, at the column support on the mesh, when the mesh gets smaller than the column, you're getting moments from those elements which won't happen in reality. And we know the column is actually three-dimensional, the slab is three-dimensional, there will be three-dimensional stresses in that area, but the model is a one-dimensional beam, a pin, with a two-dimensional piece of paper, essentially onto the pin. If you look at it too closely, the pin will just punch through the paper. Infinite stresses. You can have these singularities in your analysis model, which are not realistic. Now, problem is between the too large and too small means there is no one right answer to mesh size. You have to use your engineering judgment. Now, classic rules of thumb, the mesh size being about twice the thickness or the depth of the element is a good size. If it's much smaller than that, you're probably overdoing it, especially taking into account the inaccuracies in our knowledge of what will actually be built. And what can be good practice is run the analysis for a large mesh, half the mesh size, rerun it. Do the results significantly change? If so, halve it again and keep going until you don't get any significant change. You might get some change, a small change, but yeah, how much is the significance? Well, more than 10% difference, that's definitely significant. Less than 1%, you're within the factor of error of uncertainty on materials and sections and goodness knows what else. There is a limit to how accurate it's worthwhile pushing a model due to construction tolerances, manufacturing tolerances, tolerances on knowledge of loads and that sort of thing. We don't know everything, and we have to account for that in our design. So checklist, you know there's something wrong, run through the checklist. Look at all these wrong materials you mentioned there. Classic one, a few years ago, my colleague was doing a vibration analysis on a shopping center in Doncaster. And the natural frequencies came out considerably lower than we were expecting. It turns out he had modeled a 150 mil steel floor rather than concrete floor. And not surprisingly, yeah, it was lots different, heavier than we expected. But we knew what to expect, and therefore we spotted the error, had a laugh, and correct the model. So some examples of where things have gone wrong. The Sleipner A oil rig, I think that's how you pronounce it, from Norway. Yes, early 90s, this one. They had modeled this gravity base for an oil rig, which you can see that the 3D analysis of using all 3D elements up there. The idea here was there are a number of concrete vessels with the columns coming off it. These vessels are hollow, so they're full of air, so the structure will float. So they manufacture on land, float it out, take it in a shipyard in Norway, take it out into the fjord, let in a little bit of water as ballast to keep things stable, and then tow it out into the North Sea and then sink it and fill it up and sink it to the bottom. And it was designed for an 85-meter depth of water, or 850 kilopascals, or kilonewtons per square meter if you prefer. Very high load. Now, what actually happened when they took some ballast water in, they heard some loud bangs and explosions coming from below. They evacuated quickly, got onto the tugs before the whole thing sank rapidly to the seabed or the bottom of the fjord. And yeah, apparently it was picked up on the seismic detectors, registered as a 2 Richter scale earthquake. Completely destroyed the structure, and also PI claim of, well, in today's money, about $1.5 billion. You don't want that on your PI claim. What happens? They had used the brick elements, and which was good for overall behavior, but they then took these elements, got these shear stresses worked out the shear forces from those, but unfortunately, the model was very crude, and they underestimated the shear forces by about 50%. Now, ironically, if they had done a simple hand check, assuming, well, there's the beam, there's a fixed-ended beam, there's a UDL, what's the shear force on that beam? A one-line calculation would have told them they got their values wrong. They didn't actually check the results. They blindly accepted the model results without checking to see if they were correct or not. Plus, they detailed it badly. They knew there was a stress concentration at the areas where these tanks joined. And they thought stress concentration happens at the corners. They have a T-headed bar going just beyond that. That should deal with stress concentration. But no, the cracks just went around the end of the bars. This is why detailing for those bars should have gone right to the far side and tied into the opposite layers of rebar. Ironically speaking, they had major cracking on a previous copy of this structure, but they hadn't really realized why the cracking was happening. Yeah, if structure is cracking, make sure you understand why. Similar problem happened on the Florida footbridge, which had some major cracks, and the engineers just blindly accepted this. Fortunately, in that case, quite a few people died. Okay, another example, Hartford Civic Sensor. This was mid-1970s, quite a reasonably early use of FE analysis. It's engineering a space frame where they had made some bad assumptions. For example, the sections at the top, they assumed when they're doing the sections, the connections all noded out. Everything was built concentrically. But you see below was how the things were actually built. Eccentric connections generated lots of torsional moments in the members. Now, unfortunately, they had also designed everything using back-to-back angles, giving a cruciform section. Cruciform sections have virtually no torsional stiffness. And they also, well, they might have checked for buckling, but they definitely didn't check for torsional buckling. And the structure suffered a torsional buckling failure when snow on the roof was only about half the design load. Now, thankfully, that happened about 3 o'clock in the morning when there was nobody there, and not 6 hours earlier when there was an audience of 14,000 people watching a basketball game. That would be much more serious. But again, there were warning signs. The contractor during construction said that the roof was deflecting twice as much as predicted, but the engineers dismissed it, and so on. And there were other, yes, assumptions of restraint from the roof which weren't justified, and so on. Yeah, a lot of problems. But luckily, nobody was hurt. And then there's the CTV building, Christchurch, earthquake. Collapsed in the 2012 Christchurch earthquake. What went wrong here? Well, first of all, bad layouts. Asymmetric stability system. Big core on one side, small concrete wall on the other side. Asymmetric stiffness gives you torsion or twisting in an earthquake, which they didn't expect or didn't account for. Lack of robustness, precast columns not correctly connected to the beams. Critical results. So they had looked at story drift, the deflection of the building under earthquakes at the middle point. And the middle point wasn't moving that much. But because the building was twisting as well, the results at the corners the story drift at the corners was considerably higher than the story drift in the middle. Also, of course, checking. It was a young engineer doing the calculations, and his supervising engineer didn't supervise, didn't exercise. So young engineer didn't really have the experience. The supervising engineer who did have the experience didn't bother to check. And in this case, 116 people dead as a result. let's not go there. So time. So where might you look for additional information? So here are a couple of my favorite books. If you've not read J.E. Gordon's New Science of Strong Materials and Structures, if I don't fall down, brilliant books. Get them in a local a bookshop. These two books, I think, got me through my degree, and to be honest, I still reread them now. They are masterpieces of engineering writing, informative, intelligent, and good to read. Readable engineering books. It's unusual. I am greatly inspired by these two books. In fact, have had to replace my copies over the years. Another two books which are great to read. Why Buildings Fall Down. Yeah, if ever you have trouble staying awake at night, Why Buildings Fall Down talks about the way that various buildings have fallen down. Sometimes it's the engineer's fault, sometimes it's the architect's, ironically, sometimes even the mechanical engineer's fault. Buildings are pretty robust, but yeah, things can happen, and we need to, as engineers, we need to think about what could happen, what is unusual about the building, what's different, and make sure we account for that. And then there's, of course, the David Brom's classic Understanding Structural Analysis, qualitative analysis of structures, as you can see on the diagrams there on the cover. Here is the frame, here is the loading, and it gives you techniques for sketching out the deflections, understanding how it will move, and from how it will move to how the bending moments will be there. And of course, once you've got the bending moments, you can also then get an idea of the shear forces and so on. And really good reads. Yeah, definitely hold of that one. And then finally, hey, my own book, which has greatly been inspired by those and others. Yep, it does cover modeling, it does cover dealing with errors. We've just touched on a few things there. Also, parametric design, optimization, AI, machine learning, and a whole range of things. So is intended to be a really great introduction to the whole computing for structural engineers. Yes, a broad sweep to cover many things. With the idea then, if there's things of particular interest, maybe then giving the foundation to then go on to study particular aspects in more detail. Available from the institution website. There's a QR code there to take you to the link if you want. And yeah, at that point, at 10 to 7, see, are there any questions? Thank you much. Thank you. Yes, I think then that draws everything to conclusion.
No, I just want to say thank you for everyone attending. It was very insightful, Peter. I've really enjoyed it. I took loads of notes, actually.
All right. Well, thank you very much, everybody. I hope you enjoyed this. And yeah, any questions? Give me a shout. Connect with me on that LinkedIn. I'm always happy to chat about structures.
Cheers. Thanks, everyone. Take care.
Thank you very much. Bye-bye for now.